Hey, um, today we're gonna discuss um, a nice little probability theory problem, um, right? And today is just a word of caution for ways that you can go wrong in probability. And so the question in hand that I would like to discuss is, say you have I don't know, say 15 distinct items. Okay, let me 15 distinct items, and say you have four people, okay, and you want to distribute these items um, among the people. So, these can be apples, oranges, but they have to be distinct, right? So you care about what apple, it can be one is a bad apple, one is a good apple, and so on. You can consider these to be different cars or whatever. Um, Anyways, you have 15 distinct items and you have four people, for instance, um, and you want to distribute these items. The condition is that you want each person must get at least um, let's say one item, right? So if these are cars, say imagine these are cars and these are people, then each must get at least one car. Okay. Now, first I would like to discuss a naive way to do this, right? And I'm assuming that you're familiar with sort of basic ideas in combinatorics, but really, I mean, this is just counting. So, a naive idea could be, the naive approach could be that you are, for instance, um, you're first um, give them all one car each and distribute rest randomly, right? So you may wonder that, okay, if if the constraint that I have is that they must have at least one item, let's just give them one, and then let's just, deal with the rest in a random fashion. Um, and the way you would do this is say you want to have, and you resume in randomness. So, you think to yourself that, okay, I have 15 cars, and I choose I choose I choose four cars to distribute among all four people that I have, and that it deals with this, and I'm left with 11. So left with 11 cars, and then I can distribute those cars randomly among all these four people, right? Um, and so you can, I guess, you can think about the remaining problem as being like, sort of a bucket, and you have this car garage, and each unit that comes out can go here or here or here or here, and so it has four choices, and the next one has four choices because, again, we've met our constraint already, so we don't need to worry about how it goes about choosing this, and so on for 11 cars. Therefore, you may have 4 to the 11 possible choices to distribute these cars. Okay. Um, well, And you want to take into account one more thing, which is that the first cars that you have here, um, they could be in any order, right? So, you just chose the cars, but how do you then, pair, say you have, I don't know, a BMW or Tesla or something like that. How do you pick which one goes to what person? Um, you must take into account that as well. And so you're like, okay, there's 4 factorial ways of distributing these 4 choices that I had. Um, and if you don't like this, you may wonder, okay, um, okay, yeah, this is fine. Again, this is a naive approach, and again, this is wrong. Why is this wrong? Now, I think this is an interesting problem to think. Why is this wrong, right? Um, because I mean, the assumptions that I've made are pretty minimal, and they're really there to satisfy these conditions. So what's happening, right? And it really comes down to the following fact. Okay. Say you have, for example, say you have 5 items. Okay, so 5 cars, and you want to choose two. Okay. Now, we know that, the answer is 5, choose 2. And oh, if you're unfamiliar with the choose notation, this means just 5 factorial divided by 2 factorial into 3 factorial. Um, the way you can sort of think about it is, or at least the way I think about it is, you have 5 times 4 um, choices to be made, and then you divide through by 2 because of the order of choice, and so on. Okay. Anyways, so you want to make 2 choices. Okay. How do you go about making the choices? Well, as a naive approach ours did, we can say first, I'll pick I'll pick one item. Okay, I'll pick one item. And so what I do is I say 5, choose one, which, how many ways can I choose one item out of 5? Well, 5 ways, right? Um, so that's 5. And now I have 4 items. So I choose my second item. Okay. So I choose my second item out of remaining 4. So that's 4, choose one, and that's 4. So in total, I get 5 times 4. Well, this is 5 times 4 divided by 2. Notice they're different, and the reason they're different again is because you introduced this ordering, okay? This ordering of choice. And, I mean, this is a reasonably easy example if, for example, I had more different constraints. So I had to, for example, have them at least get 2 items each. You would have a harder time accounting for the ordering that you introduced by this naive sort of, picking and then picking again way. And so you want something more reasonable, right? Um, so how do you how do you go about thinking this? Well, again, one of the things that you need to take into account is, um, to not have any underlying, um, ordering, right? Um, and usually the way you do this is, um, you first define sort of smaller events that you can deal with. So say you have, again, 4 people with their garage or whatever. waiting for the cars on the assembly line. And you say, okay, this is my person 1, 2, 3, 4. You define event E1, for example, to be the event. You can find it for this condition. Even is E1 is the condition where first person, say, does not get a car. Okay. E2 is the condition where the second person does not get a car. E3 is the condition where the third person does not get a car. And E4 is the condition where the fourth person does not get a car. You may want to then say that what we want is an event E that is E1 not happening. So this should not happen, right? And this shouldn't happen, and this shouldn't happen, and this shouldn't happen. Okay. Or you could have thought of it as a different approach. You could have said that, okay, E1, I will define it as the first person does get exactly one car, second person get exactly one car, and so on. Or the first person gets at least one car, the second person gets at least one car, and so on. It's usually easier to think about, you can easily define these because these implies that the first person gets 0 cars, and this also implies that the second person gets 0 cars, and so on. It's easier to define it, but at the end of the day, it doesn't matter. But what you can now do with this is you can realize this is equal again the intersections of conjugates or complements is the complement of the unions. Okay. Okay. So then this becomes my event. Okay. Cool. Now, what do you want? You want the probability of this event. You want probability of E. And okay, to find the probability first, let's define our sample space. So what's the total number of ways that you can distribute things? Well, there's 15. Again, now you really don't care about whether someone gets it or not because this is the total sample space. And so you have, well, 4 choices for 15 things. So this is 4 times 4 times 4, 15 times. So that's 4 to the 15. Okay. Now, P of E is, notice that E is whatever this is conjugate, right? So P of E will be 1 minus P of E1 union E2 union E3 union E4. Okay. Interesting. And now the problem is, okay, how do you calculate the probability of unions of simpler subsystems? So we know what this is, right? How do you calculate probabilities of simpler subsystems? Well, it comes down to this thing called inclusion-exclusion principle. And it's kind of a nice name in my opinion because it tells you exactly what the idea is. So let's say you want this color, right? So the intersection of all 3 events. Well, what you would first do is you would have all of these added together. right? But notice I counted this region twice. And so now I want to subtract away this region and this region, this region. So they're pairwise intersection. But then I subtracted it twice again, so I must then add it. Um, and so, yeah, I get this. Okay. So if I want the union, I would have first um, added this and that, but I would have double counted this. So I subtracted, but then I double subtracted, and then I added back. Right. So in other words, this would give you um, the following sequence of sums, right? So the first sum would be your probabilities of individual events. Okay? Then you subtract the sum of pairwise intersections. Okay? And then you add the sums of probabilities of, um, you know, the triplet intersections. And then you finally subtract, and there's just one term, so this is the probability of um, e, E1, E2, E3, E4. Okay, cool. Um, and so now we can calculate the probability, but we want to now, first compute what is EI. Well, for any given I, is the probability that the ith person does not get a car, which means he gets 0 cars. Okay, now how can he get 0 cars? Well, you can distribute 15 cars not to the first person or the ith person, and only the other 3. So that'll be um, instead of 4 to the 15, that'll be 3 to the 15, because you have 3 choices. Divide by 4 to the 15, your total choices. Okay. Now probability of EI, EJ, right? So the probability of the first person, for example, not getting, and the second person not getting, right? So that'll be 2 people not getting the car, right? So you may want to remove this and only distribute the thing over here for 2 people. So now you have 2 choices, and this, and I guess you can reason now this guy with 3 people not getting the choice for the car, only one of them, and this is just 1 to the 15. Again, you don't need to have the 15 because there's just one way to do 3 people for 3 people to not get a car, which is that the 4th person gets the car, and then P of E of EI or E1, E2, E3, E4. This is 0 because there's no way that we must distribute the car somewhere to someone, right? This is 0, so we don't count this. So we can discard that. But there's one more thing that this is hiding, right? So what two people of these? Well, these are generic I and J, but they could have been your um you know they could have been your first and second, or second and third, or first and fourth, and so on, right? So when you're summing all these probabilities, I mean, for any 2 people that you fix, sure, this is the probability, but then you must add it for every such pair. Well, how many pairs? How many many ways to pair. Oh, it's just 4 choose 2, right? You choose 2 people out of 4. So the way you would do this now, right? So this final probability is 1 minus the sum of, well, first you just, sort of pick one person out of 4. So there's 4 choose 1 ways to do this, times 3 to the 15 over 4 to the 15 minus, you would do 4 choose 2 of 2 to the 15 over 4 to the 15 plus 4 choose 3. So now you're choosing 3 people for the triplets. And so again, there's 4 ways to do this because again, by the symmetry of choice, you can either choose 3 people to consider to not get a car or 1 person to get the car. So this 4 choose 3 is the same as 4 choose 1. Again, the reason being that it's n choose k is n factorial divided by k factorial times n minus k factorial. Well, if you have n minus k, then n minus k is just k. So these are same. Okay. Yeah, and that is 1 to the 15 divided by 4 to the 15 minus 0. And that is your final answer. Again, we made no assumption of choosing one person first and the second person next. I mean, well, you can you do define events, and you do things with the events, but there's no underlying, and it's a subtle point. It's a subtle point, and you may not be convinced. So how about this? We run a simulation, right? How about that? And let's see what we get out of a simulation. So first, let me open up Julia. I don't know if you guys know Julia, but it's an amazing language. I love it. Let's calculate what the probability here was, right? So we figured, oh my god, this is going to be a big number. But since it's okay, it's not terrible. So the probability here that we calculated is going to be 4 factorial times 5 choose 4 times 4 to the 11 divided by the sample space. So that's 4 to the 15, and you can see that these cancel quite a bit, and so we can do that. Let me define a choice function. Choice and just k would be Oreo of 1 divided by Oreo k times Oreo n minus k. Okay. For instance, we know that 5 choose 2 is 10, which matches this. Perfect. Now we will say that the estimate 1, since we're defining events, estimate 1 was the following. It's factorial 4 times 5 choose 4, or rather 15 choose 4. That's what I meant. 15 choose 4 divided by, right? So you get 11 here, 15 here. So the difference of 4, right? So you get divide by 4 to the 4. Oh, what did I do wrong? Oh, oops. I didn't define this as choice, and that should not be true. Um, because yeah, the probability is more than 1. So certainly that is not true. Um, so we know there's a problem here, right? Um, again, you're double counting because you're sort of having this underlying assumption of choice. Remember how once we made this choice, we got basically double the number here, right? Okay, cool. So let's see what this gives us, right? This will be 1 minus bracket 4 choose 1 minus 3 to the, or for numerics, I should do this to the 15 minus 4 choose 2 times 2 over 4 to the 15 plus 4 choose 3 times 1 over 4 to the 15 and minus a 0. It doesn't matter. Okay. Good news is it's below 1, so it sounds like a probability. And okay, it seems quite high, and it seems like, yeah, sure, if we have 4 people, it's going to be hard to sort of, you know, get one item to not be in one of them. Right? It's going to be a lot smaller fraction than the total possible ways. But I would like to implement that as sort of a simulation, right? So let's do the following, right? Um, I can define a function, or let's have some fun first. Let's do this one run. So say I have items equals the vector, say 15 numbers, and I have my people, and well, people have say, um, or yeah, let's let's make people sort of addict, right? Um, sure. And then I'm going to say, okay, people A equals, or okay, let's make people a list of peoples. So A, B, C, D, and I'm gonna make, okay, um, the fig be my dictionary, and I'm gonna say, okay, config for I in people, I would have configs type ei be a vector. Okay, cool. Now what I want to do is I want to randomly pick these elements one at a time, right? I'm gonna say L equals length of my items vector, And then I'm gonna run a for loop, or rather, a while loop. So while L is not equal to 0, um, I want to randomly pick things, right? Um, so I want to randomly pick things. Oops. So I want to say, okay, my index equals rand from 1 to the length. Okay. And then once I have an index from my items array, I am going to have, I guess, randomly pick a person, right? So rand person equals rand people. And then I am going to say push inside the config rand person vector, push inside it the items index element, and then I'm going to delete at the items index. Or, well, I don't know how items or delete at works. I think it should be this. I think so. Just make sure, yada yada. Oh, and L equals the new length of my index array. And then, yeah. Oops. Let's see what happened. Okay, it did something. It returned some error. Attempted to access this, index that. So, okay. I don't know what happened here. Let's debug for a second. So we have length not equal to 0. So we have this working, until my length is 1, right? So while my length is not equal to 0, I do this, and then my length, I read out my length of my index vector. And assumably this was 1, so we add an item, and then, yeah, and then, okay, let's see, items is empty, yeah. Then L add a new length for the index, so it presumably became 0. I don't know. Uh, let's again. So it's 15 seconds. So, okay, I mean, this should be it, but okay. So I do this. Yeah, maybe I want to have my length updated beforehand. I mean, it shouldn't matter, but okay. Items. I see. Oh, let me take a look at that. Oh, there we go. I caught the error. This must be items. Okay, perfect. Um, Regardless, um, this is what we have. As you can see, um, again, I filled this many times, but yeah, well, things were double counted. Let me package this into a function and we can run this again. We'll call it simulate, and let's have the number of items be n, the number of people be m, and the minimum number that I want people to have to return this as true be a. Right, so I'm gonna again say, okay, items equals 1 to n, and then I'm gonna say people equals, well, I mean, it doesn't matter, but sure, people equals um, vector of 1 to m, and then config equals dict, and for person equal, I would have config person be an empty vector of type any, doesn't matter. Anyways, okay. Cool. So we did this. Now we should have a length of items, not index. Oh, interesting. I see what happened. Interesting. Okay. We can worry about that later if things don't work. Anyways. And then yeah, that's it. Yeah. We can have this. Perfect. But instead of index, we want items because we don't want typos. Oops. Just trying to make things tidy and neat. Okay, perfect. Right. Now I want to, okay, first let me, um, I guess, okay, I'll just do this, okay? So um, for person in people, for person in people, if if the length of the vector config of the person is equal to 0, right? So if the length is 0, so if the person got nothing, I return 0 comma config. Um, okay. Else I just return, oops. I mean, not oops, but sure, I can have a false, and here I can do true config. Okay. Can I sim 15 4 and 1? True. Interesting. So this is how distributed. We had 1, so person 1 got cars 1, 6, 11, and 10. Person 3, again, these are dictionaries, there's no ordered, but well, person 2 got cars 3, 4, 5, 3 got 13 and 8, and 4 got 2, 7, 9, 12, 14, 15. Okay, that seems like we made no issues there, no errors there. I would want to guess activate one of my packages, use a plotting package, and then what we want to do, and this is the fun part, is we want to simulate this happening, um, I guess, a lot of times, right? And so what we're gonna do is we're gonna say, okay, and okay, let me calculate P of um, NK NMK equals sim of 15 NMK, the first element that it returns, divided by the total number of ways that we can do things, which is m to the n, right? Um, or okay, now this is not true because this will just be one run, and we don't want the probability over many things. So what we want is we want to say, okay, first let's run like many plots, right? So we would say, let's have simulation runs equals for I in 1, 2, let's say 100. So we do 100 such simulations. Okay, that's why I like Julia, it's fast. Then we want to have the hist of of or well, maybe we don't want to have hist, but for now we can just say, okay, count is equal for I in for we in simulation runs. Oops, is equal to true or just 194. And hold on, up there from what I remember, we had lo and behold gotten 94.6%. So I'm happy. This is great. This is a good experiment. I want to see if it converges over long things. So what I'm going to do is the following, and this is what I love about Mach-E. Mach-E is the plotting package that I'm using again. So using GL Mach-E, I'm going to create a let's say I keep track of my P, which is my observable, of my, say, a value 0. Okay, I have this. And I'm gonna have p equals the observable of p. Observable lets you sort of keep track of it and update it without really dealing with it. And okay, interesting. Let us now think about what we want to do. So we want to run this and keep updating p, right? Okay. So I want to let's work out the map, right? So say at nth step my probability was say alpha percent or just alpha for n plus 1 or well, you know what, let's brute force it. Right, so I'm gonna have a true sums equals 0.5. Yeah. Okay. And so I'm gonna do the following. I'm gonna say for let's say this, right? So n equals say 1,000 for I in, or let me make first the scene, right? So I'm gonna plot, gonna lines p. Okay. Okay. E equals observable a vector with the number 0. Okay, now I'm gonna have for this line's sake, let me add one more, and I'm gonna have lines p. Oops. Okay. For now, our probability is 0. You will notice that, you know, if I now say I push into p value 0 and I notify p, it'll update the line. I mean, wasn't obvious, but updated it. We can center it, the thing again, to update it, but okay. So we're gonna call our scene equals lines of p. Okay. And now I'm gonna run the following loop. Is it for I in 1 to n, so for iteration in 1 to n, I'm going to say that my true sums plus equals count is equal or yeah, is equal we 1. Okay, let's say so I'm running things for just one iteration. Okay, I just need the first for pull j comma 1, or I just need, yeah, say if if run simulation, sim 15 for 1 first value is equal to true, and say true sums plus equals 1. I'm gonna add 1 to n ones. I'm gonna calculate the new probability. Push into p, the value true sums divided by n ones. Notify going to center the scene, and voila, I think this is it, and we should enjoy the entire scene. So for I in 1 to n, so I run 1000 iterations of running the simulation, checking if the first thing is true, and if it is true, then I do this, and okay. Whoops. Okay, should be probably dot fake scene dot figure or x. I do not know. Figure center scene dot figure. So it's the axis. Is it figure dot x? I know you can do something with this. Yeah. I mean, hey, I just centered it, right? I centered it just before this. I swear to God, I centered it. Right? Read the docs. Oh, okay. Cool. Let's say that S is instead. Okay. Perfect. Hmm. Okay. Give me a few minutes to debug things. Scene dot scene. No. Scene dot figure dot x. Figure dot x. Okay, how about this? I create God damn it. I'll have to ask Google, I think. How to center geometry figure. Okay, let's look at AI. Resize to layout. Okay. Let's see. No. Oh, yeah, of course. Okay, perfect. Now we have something. Let me reset all things. And let's watch the show. Okay. So I defined my observable, define this. I already have this, didn't change that. I want to say that my scene equals lines of P. Okay. And I finally want to run the following, and I want to center my scene, or rather want to resize layout the scene dot figure. You ready? Let's go. Uh-oh. Okay, that makes sense. This has to be 0. Optimizing. Okay. Um, okay. Yes. And then I want to do this. Perfect. Cool. Although I will do this again just to have that dramatic effect. And this time I will not forget to, maybe sleep for 0.01 seconds. Okay. Look at that. Isn't that cool? If you look at what that is around, that seems about 94 point something to me. Yeah, I can run that more, but I think it'll be more interesting to see um, some other simulations. So let me have this, and I guess what I would want you to predict is um, whether, so what happens if if I just have this thing changed. So instead of maybe 1541, what happens if I have, for instance, I guess, um, 7 entrees, uh, 5 people, and then everyone should. Okay, let's make it interesting. Let's do 12. I like the number 12. Let's do 7, and then I want to make it 3. And so this has to be closer to 25, say, or let's say 52 number of cards in a deck. Come on, make your predictions. Higher or lower? And here goes. Ooh, just dropped down. It's really close to 1, I suppose. So the number of ways where you can have 52 cards distributed among 7 people, where everyone must get at least 3 cards, is very high. Okay, let's do a different iteration now. This time, to make it interesting, let's say that, okay, you have a deck of cards, you want to distribute everyone at least 7 cards, and I have 3 people playing the game. Okay. Yeah. So if you have 3 people, you randomly shuffle cards and then, I guess, put it into baskets. What is the probability? Okay, it's still really close. Interesting. Let's stop it. Yes. No, that I stopped it. Probably should let it go there. Anyways, I'm gonna bring it down. Let's say that um, I now want 7 cards and I have 4 people playing. 4 sevens are 35, or let's say 5 people. 4 sevens are 28. 5 people playing 35 cards. There should be enough cards, certainly. But let's say, 7 people playing, and I have a full deck of cards. I want 5 cards each. Um, or sure. Um, I think if you realize something, the problem is symmetric in the people and cards, because you can define the problem to be the cards pairing up with people or people pairing up with the cards. It's the same problem, so it should be symmetric in that aspect. I think that's why the previous probability was close to 1 both times, because I just swapped the numbers. So yeah, I think again you can have 6 people, or I even forgot the number now. But yeah, I think 7 people and 6 cards. And wow. Okay. So I suppose you have, with 52 cards randomly being distributed, you have the card distribution be very equal, which is why it's highly likely that you will get indeed at least those kinds of things. So I think if we play with, I guess, a smaller deck of cards, so say you have instead a deck of, what's the next best number? Well, I like 12, and you have 3 people and you want at least 3 cards. It's possible, but well, you can also not do it. Um, ooh, interesting. I liked that curve there. Okay, interesting, interesting. Um, ooh, you can do one. You can do an interesting thing, right? You can do the following. You can have a problem where, so this is called the hat problem, but okay, I don't want to redefine things, so I'm gonna do my version of the hat problem. There's 12 people, 12 hats, and each person must get their hat. Okay, what's the chances that on a random assortment, each person gets their hat back? Okay, it's gonna be super low, right? It's gonna be like a bogus sort kind of thing. Um, um, an interesting question is, what's the probability that no one gets their hat back? Again, something similar to what we did. You can apply inclusion exclusion by defining some smaller events. For example, you can define E1 to be the probability that the first person gets their hat back. Um, but yeah, fun fact, the hat problem I just described, in the limit that number of people get to infinity, the hat problem becomes, the probability becomes 1 over E, which is about 37%. Um, it's kind of, one of these constants in probability, 1 over E. You see the 37% rule in picking life partners, romantic partners, and things like that, or maybe candidates for your company or something. It's interesting. You can take a look. But like, let's do 7 people, 7 hats. What's the probability that each person gets their hat right? Um, let's think about it, right? Um, I predict that there's 7 factorial ways to do it, right? And only one of them is right. So the probability is 1 over 7 factorial. To get some reasonable number, let's pick 4, right? Because 4 factorial is 24. So we should see about 1 in 4 times this should be right. Okay? Wow. I was I thought this is gonna be true. I'm gonna have a correct prediction, but interesting. The problem here is, um, yeah, it's more like 1 over. It's 1/10. Interesting. Um, I mean, I thought the problem is going to be 1 out of 24, right? 4%. Oh, yeah, not 1 in 4, 4%. Yeah, I'll have to think about this. So I'm saying, okay, 4 people, 4 items. I want everyone to get at least one, which means everyone should get their hat back. Well, how many ways are there to assort everything? There's factorial of 4, which should be 24. Yeah. And this is the total number, and the possible ways that you can have, or okay, let's think it on paper. So you have A, B, C, and D. So you shuffle these around. What's the probability that it gets back to A, B, C, D? Well, only one possible correct answer and 4 factorial possible shifts. Yeah, 4 factorial. Either my probability is fitting wrongly for the given simulation, I don't know. It's an interesting problem. Okay, anyways, that was it. And yeah, stay curious, may the kid remain, and yeah, be cautious of the assumptions that you make for probability. And yeah.